Muy buen dia, good morning, afternoon, everyone. I'm André Diniz da Silva. I work for the National School of Statistical Science of the Brazilian Institute of Geography and Statistics, IBGE. And I'm leading the UN Regional Hub for Big Data and Data Science in Brazil, serving Latin America and the Caribbean. This is really a great pleasure to be here to open this webinar. It's a webinar of a series. We name it Road to Festival de Datos, which will be held in Uruguay from 6 to 9 November this year. The Festival de Datos wants to connect people and communities in the data space, serving as a platform for announcing new and impactful collaborations to unlock investment and drive innovation. I will leave the link to Festival de Datos on the chat. Please visit, register, and participate. It's going to be in Uruguay once more in this first webinar of the series of 3 webinars. It's organized by the UN Regional Hub for Big Data and Data Science in Latin America and the Global Partnership, and with the support of ECLAC via Knowledge Transfer Network. The second webinar is going to be held in 6 September, and we will discuss the web scraping for price, the use of web scraping for price. Brazil and Chile will give us the pleasure to share their experiences with us. The third and the last one is going to be held in 11 October and will be held by us and with the Dominican Republic and Paraguay on the use of big data science for statistical production. After this short introduction, I will just give the floor to Rolando Campo, who is the current chief of ECLAC Statistics Division and will be the chair today. Rolando, you have the floor. Thank you.
Muy buenos días a todos ustedes.
Good morning to all of you. It's a pleasure to be here in this event, in this webinar in which we are heading the Data Festival in Punta del Este, Uruguay. It's a global data festival that will be carried out or held in Uruguay next November. And as Andrea said, we will have a webinar that has to do with big data for statistics in Latin America and the Caribbean, and with also some presentations, 2 other presentations that we will have about the use of the observation of the land for official statistics. It is a pleasure to welcome our 2 speakers. The first one is from Mexico, from INEGI in Mexico, and the second one is our colleague that comes from DANE, from Colombia, and I will give them the floor later on in this webinar. Before we start, as you all know, we have interpretation to English in this webinar. You can select the option on the lower part of your Zoom platform. Without further ado, I will now give the floor to our colleague from INEGI, Gerardo Esparza, who will present to us his talk. It has to do with geostatistics and data cubes in order to monitor the national statistics. Mr. Esparza is a professional in informatics and space data. He is currently the General Director of the General Department of Geography and Environment of INEGI, and as an attached General Director, he coordinated the making of the national cartography and also the digital map of Mexico, which is a tool that is very useful for Mexico, which contains all the data and geographical layers that are compiled in the national territory. In the international scope, they also participate in working groups with the Committee of Experts of the UN regarding geospatial data, UNGIN, which last week had its meeting, its global meeting in New York. The results were amazing, and there was an attendance of more than 78 countries in the event in New York. So without further ado, Luis Gerardo, I give you the floor for the next 15 minutes so that we can have enough time for questions and answers. The floor is yours. Thank you, Rolando. First of all, welcome to this webinar. It is a pleasure for me to be with you and to share a little bit of what we are doing in Mexico at INEGI with these very interesting topics. I also wanted to thank the organizers of the event, and on behalf of Dr. Graciela Marquez, President of INEGI, she sends her regards, and she wishes that this webinar and the next ones covers 3 big topics to be covered in a general way, but this so you understand how we are managing this at INEGI. First, the data cubes. You will see how we are working with remote perception and what we are doing with this. Then the geostatistical framework, which is our key in order to compile all the statistical information. And finally, novelty ways to publish or post the statistical information through networks. And now, regarding data cubes here, I won't get into the theory, but all of this is based in data cube. Data cube is, well, perhaps many of you know, started in Australia with all this current. We had the chance at INEGI to go to Australia to learn the techniques. We were taught about this, and now there is a very big current in this regard. What is this based on? We need, first of all, satellite data, satellite images. We need that input. We also need to have a file system that allows having or knowing where the images are stored. It should be indexed so that this can be accessed quickly, and all the support of the ODC core. And there are different tools that have to do with international standards, some of them with specific languages or components in the software in order to exploit this information. This in a very general way. In the Mexican case, let me show you. What we have in Mexico now implemented is this data cube that is based, or which has inputs which from these Landsat images from the year 82 to date. And we currently continue to update and to feed our servers on a daily basis. You can see here that for every sensor of Landsat, how many images we have and for which years. But to date, we have 139,000, more than 139,000 images stored and structured within the scheme that I showed on the previous slide. Here, what is important to notice is that as the years pass, the amount of images increases. Now, you have to remember that the Landsat images nowadays have a resolution of 30 meters. We're working on that. So what are we producing? What we are producing is, to date, 3 main products, sub-products, based on the processing of that data cubes. We have a geomedian, we have an NDVI index, and we have water observation from space. What is each one used? Well, the geomedian is an interesting product because it pixel by pixel takes a period of time that is defined, and at the end, the result of each pixel is the mean average that it had during the whole period that we define. It could be a month or a year. We have now published 3 versions, and every year we are issuing a geomedian, a yearly one. This is a clear idea, or gives you a clear idea of what most of the time happened in this territory with this geomedian. We also have the NDVI, which is the index of normalized difference of vegetation. We have also posted this at a national level. This is available for the public. We can estimate the quality and the amount of vegetation. And we also have the WOFS, which is the water observation from space. We also update it every year. We have published 2 versions at the INEGI, and this allows to follow up on the behavior of the bodies of water to see if they are reducing their capacity or not. These are the three main products or outputs that we are producing with the data cube. We also have a potential use that we are now analyzing. The idea is, well, at INEGI, we are producing, besides the statistics, the national cartography, we are trying to find out how we can identify with those images and using the data cube and all the core of tools to identify changes in the territory. This is important because it allows to join our efforts of cartography to the places where the changes occur. And the advantage of this technology is that every pixel is analyzed individually, and it is possible to have, in addition to the 30 meters observation, the changes. We can detect the changes that allows to determining that there was a growth in this locality. We have to go there and make a survey or our cartography or gather cartography data. That is what we are planning to do soon and to incorporate it in our outputs. Now, we are producing those three outputs of the use of the data cubes that I show you, the GeoMedium, WFS, and the index. Well, how are we implementing this in data systems that are regulated at the INEGI? Well, first of all, we are working with a new version of the series of the soil use and vegetation. We are improving the normal or current scale. We are also using the GeoMedian for this as a basis or baseline, and using algorithm of data science and all the machine learning and all the networks, etc., in order to use this technology to automatically generate our national data at a scale of 50,000. This means that we will increase the resolution in 6 months. This is being published this year. And now, regarding geohydrology, we are analyzing the bodies of water and other issues there. We are using the WOFs as a baseline in order to analyze this product. And we also have soil cartography. We will use the GeoMedium as well as NDVI index in order to evaluate this and to issue a national product. We are working on this, and what we are doing with the data cubing has a direct repercussion in outputs that are calculated through the use of this GeoMedian and other outputs, as well as some other derivate products that use all these inputs. Well, basically that here we have what we're planning to do in the future. We will continue using data cubes. And a question that we get is, well, if we are working on incorporating Sentinel images, which are of 10 meters, this has a better resolution, and this will allow us to determine and detect things with closer or with more detail. When we change from 30 meters to 10 meters, well, we definitely have an increase of the data. Now I'll give a quantic leap. We were seeing how we're working with the satellite images, how we have data cubes, and how we generate intermediate outputs that allow us then to process the information and make regular analysis. But what do we have for the integration of this geostatistical data? We have this geostatistical framework. Perhaps you have heard about this in other meetings. It is very interesting because actually it's a cartographic product, but a cartographic product which intention is to have codes that every cartographic object that the system uses should have a code that is you cannot repeat it, and that means that with that code and all the data produced within the INEGI and outside of INEGI can be put in the space, in the territory immediately. Something that we have said that is very important, which is to know what is happening in socio-demographic and other aspects, but this allows us to know where everything is happening. This is a very straightforward component. Let's see how it is built and incorporated. This was created in the year 1978. It was more a crocus than a cartography, but its purpose was always to have an element that allowed to see the statistics represented in the territory some way. In the year 78, it was, well, technology was not as advanced, so it was basically a crocus. So it has evolved, and well, I will show you the progress throughout time. These are the components of the framework. We have the national territory. We have divisions that are called state geostatistics. These are ACEE. Wherever there are no political boundaries, we have to place some political boundaries in the AGEM. But in the other ones, there are no political divisions, but some other divisions that we have made. As you can see, we do have those political divisions in the ACEE, and in the AGM, we have the other types of divisions. We can even get to the specificity of localities, even blocks, where we have urban or rural localities, which blocks we even have the block identified. And each of these elements has a unique code, which is irrepeatable, or it is non-repeatable. With this code, we can place a person making a survey in the territory, and you can see the result of this survey. You can now put it in the space where it corresponds, or in the location. This is the evolution that we have had since the 80s. And when was it used in the 80s? You can see the details of how it was used in the 80s. The maximum level was the locality. There was no more detail. We have progress throughout time, and we now have the blocks identified to know from what number to what other number of the block it gets to. This has been the evolution of the product throughout the years. It is highly used because all the information produced by INEGI or the state use this framework in order to locate their statistical data in the territory. We've already talked about the product that we have at a national level in order to georeference the information. What happens with the publication? Because, well, that's another important topic. How are the statistical data made available to the users? For that, we have the traditional method. Well, you know, this theme maps, and through this regular network, which is regular because this refers to quadrants of different shapes and sizes, which corresponds to how the territory is made up in terms of its political and administrative boundaries. And well, this is the regular network, and this is how we publish everything regarding the census. This is an important issue because we are analyzing new ways to complement these representations. Here we have a map of the total population. This is a result of the 2020 census. The darker colors represent a greater population. This is a municipal map. Look at this area here. The darker areas is where we have greater population. Here we have a municipality called California. And here, apparently, we have a populated municipality. But what happens with the greater detail that we want to analyze so that we can have a homogeneous comparative of the statistical phenomenon? Well, for this, what we have nowadays are the regular networks, but we have many implementations of those at a regional and also at a local level and at a national level. And what we did at INEGI was to investigate all these elements, and we found that the Open Geospatial Consortium, which is a very important consortium that produces open standards, worked and designed a standard, which is the DGGS, the Discrete Global Grid System. This establishes a global grid worldwide, and it has tiles or quadrants of a regular size and whose determination is not repeated. This allows to have a comparison and an interpretation at a global level. So let me show you the three implementations that can be done with this standard. These are the three designs that we have, which cover the whole globe. We made some research and we adopted the quadrangular, which is this one, this standard, which is RealPix projection. It is not new. This projection was already used specifically in science and research of high level and advanced math. And it is a very important and interesting projection because what it does is, well, it covers the whole globe in a cube, and what is projected in the cube is then shown in the territory in a map in this way, as you can see it here. This is the projection, but if we put the globe in a cube, this is what it shows, and the first cells of the first level would be here, and as of there you can make a segregation based on the cells. How does it save the comparability? Each cell can be divided in 9 cells. Each one of them has a classification, and those 9 cells can also be divided in 9 other cells. It always has that correspondence. We can get from the greater level to a lower level following that same relationship, and we can go up and down in those levels without any problem. In Mexico, we have already adopted this. We have a grid which is at a level 4. From level 4 to level 9. We don't get to level 10 because we would start having problems regarding confidentiality. We have a cell here. This is level 5. How do I know? Well, because you can see the numbers here. The number of digits means the level that you are in. Here you can see that this number has 5 digits, so this is level 5. And if we divide this cell in the next level, what we have is that it adds a digit to have these cells perfectly identified, and that's why it's possible to get to the minimum level to the greater level and vice versa. Every cell has the same space and it's at a global level. So what have we done? We have already processed in the grid 2 census, the population census 2020 and the economic census 2019. We are about to start working on the economic census 2024, but here in this level 5, we have the population. Remember that I was talking about this space in this municipality. We saw the whole municipality with that level of population, but when we get to a grid level, we get to specific homogeneous areas, and we realize that here in this municipality is where the population is concentrated in this area specifically. For some analysis that need a very high level of precision, this allows to locate a phenomenon in a very precise manner in the territory. This is what we have, and this is the map of the population at a level 5 of the grid. And as I said, we've already worked on the population and economic census, and what we have put for each quadrant, well, we have given it a characterization. For instance, in this cell, we can know that is a cell 8. We have that, well, in this cell, how much population we have, how many men, how many women, how many are over 60, the number of houses, and the number of economic units, which are the businesses. Also, of those 76, how many are retail stores, how many cafeterias, ice cream shops, and whatever you need or you want to see it here are placed here. So you can have a characterization which is very detailed of each of the cells. As I said, this is important to make spatial or reduced statistical analysis, and this has great potential. We have already posted in the INEGI website the grid as an infrastructure. I mean, the grid with all the divisions of its quadrants, documents, methodological documents of what is produced and how it's produced. And this year, we are close to posting or publishing this grid you see here with specific place for the grid. We will post it or publish it this year, and it will be, or it will have statistical publications in this grid, and the coming census will be posted or published within the grid as well. So that was all within the geospatial part, as you were saying, how to integrate the statistical and geographical information.
impulsar,
which is something that has to be highly promoted within Latin America and the Caribbean, as well as from CEPAL. At CEPAL, we are trying to see how to succeed with all these. Congratulations for the progress you've made with the grid. In the end, this can be of great help. Let's move on now to the next speaker that comes from DANE in Colombia. He is Carlos Alberto Duran. His talk has to do with the use of land observations for monitoring the Sustainable Development Goals. Carlos Alberto is the coordinator of the Internal Working Group of Research and Development of the Technical Department of Geostatistics in or at DANE, the Administrative National Department of Statistics. He is an engineer, a cadastre engineer from University Francisco José de Caldas in Bogotá. He is a specialist in spatial analysis from the University of Columbia. He has a master's degree in applied statistics from the Santo Tomas University in Bogotá, and his work is focused on research and, well, that covers the analysis and statistical modeling and spatial modeling, as well as geovisualization in topics related to social demographics and economics. The progress that DANE in Colombia has made are focused, and well, it's very good that we have today Carlos Alberto with us in this event. Carlos Alberto, the floor is yours for the next 15 minutes. First of all, thanks to the organization for inviting me to this event. I will start sharing my screen right now. Basis of the land for the monitoring of the SDGs. And I will specifically focus on two indicators that use the satellite images for their calculation, which is point 11.3.1 and 11.7.1 in Colombia. The presentation has 4 sections, which are very straightforward: an introduction to the indicators, the methodology, the results obtained, and the conclusions of this work. As an introduction, we consider that it is very important and fundamental to integrate the statistical information and geospatial information because it has different scopes of application. The first one is the process of decision-making at different levels, which is something that perhaps with the separate information, geostatistical and geospatial, cannot be achieved. Now, with this integration, what we can do is to get to details that allow having a more efficient decision-making. The second point is the measuring and monitoring of the SDGs, Sustainable Development Goals indicators, and also the integration of this information also allows the exchange of data between institutions. We know that in many countries, the statistical office is separate from the geographical data office, and therefore this integration allows the data exchange between the different entities. We will also produce new knowledge and integration of the data. Separate information cannot achieve this, but by integrating this, we can have this new added value, this new knowledge by integrating these sources of data. We will also promote the investment and development of capabilities because all of this is focused on the integration of these two sources and obviously examine new sources that are always appearing in a very robust manner in order to extend the calculation of the SDG indicators or determining other type of data and added value. Some key benefits of applying these land observations, specifically in the statistics office for calculating the SDGs. The first one is the possibility of derivating indicators that other way wouldn't be easy to calculate. Based on the initiative that the UN has, as well as the data integration groups, we have discovered that there are some indicators that definitely need the use of geospatial as well as statistical information integrated, as we will see it later on. At the same time, we also know that the statistical information is gathered in a massive way in census. These are not collected individually, but massively based on surveys, which have less representation than a census. So the geospatial there comes in to support this proportion of data of a greater coverage with greater disaggregation. And obviously with the integration or with the use of land observations with satellite images or other geospatial or spatial data, we can get to the details or more specificities regarding the indicators, ensuring that these indicators are guided spatially and that this allows making decisions or carry out actions which are more focused if we compare it to having results at a national or regional level. Getting into the specific indicators that we will address here, well, first of all, we have to mention that the objective 11 is guided to the cities toward making settlements to be resilient and inclusive. And this is an indicator that is focused on this. When we talk about cities, we're talking about a greater or more detailed scale. But if we compare it with other indicators of the SDGs, here we have two goals, 11.3, which is guided to urbanization, which is inclusive and sustainable, that ensures a coordinated planning of the territory, and 11.7, which is guided to the universal access that the people should have to these spaces of welfare, green spaces, safe public spaces, inclusive, accessible, and to specific parts of the population as well, so that they can have access if they are disabled. We have used the indicators 11.3.1, which is the relationship between the rate of consumption of the soil and the rate of the population growth, and the indicator 11.7.1, which is the proportion of the built surface that is used as an open public space for everyone, and which is divided by or used by this population of interest. There is a custodian organism that defines the methodology of how this can be calculated. In this case, is UN Habitat, which is the custodian of these indicators. And the SDG indicators has like some tiers or some typologies according to their development. In this case, both indicators are in level 2. What this means is that there is already a clear methodology or metadata established, and there is a process that can be carried out, but the data are not produced regularly by the countries, mainly because in a certain way, we are entering this new matter of being able to implement new data sources that allow getting to the calculation of these indicators. In that same sense, and getting into these specific matters, what we did in Colombia for the calculation of these indicators, these two were calculated on a universe of cities, and there is an important clarification to make here. We determined the universe of cities based on a standard international methodology defined by the European Commission and the FAO, and which the UN has already determined to implement, which is the degree of urbanization, or the curva. Based on the size and density of the population, it would determine the universe of cities in every country, and this would allow the results to be comparable regarding the indicators in the countries. In our case, in Colombia, this universe determined 68 cities, and for the calculation of this indicator 11.3.1 from a period from 2015 to 2020, it was done on 63 cities that had satellite images of good quality. For the next indicator, which is a little bit more robust because it needs to define those open public spaces and a greater amount of data sources, there is also a recommendation of the GURBA, which states that you can have a representative sample of the cities, where for this case, we decided to make the calculation on a sample of 9 cities of the 63 cities where we had initially calculated the 11.3.1. Here we have the list, the distribution of cities in Colombia where the calculation was made of the indicator. The inputs for calculating the indicators, well, for 11.3.1, we have the projections of the population. We know that the indicator is a coefficient between the consumption of the soil and the population growth. Here we have the projections from the census 2005 to get data for 2015, as well as the data for 2018 for getting the data for 2020. The delimitation of what is urban area in order to be consistent with our political divisions. This is what has been defined in the geostatistical national map, and we use Landsat 8 images for the year 2015 of 30 meters and Sentinel-2 of 10-meter resolution for the year 2020. Sentinel-2 were not used in the two periods because Sentinel-2 was liberated for the use of the public as of the year 2017. Therefore, we use Landsat 8. In the case of 11.7.1, you can see that there is a greater number of data sources. We have the groups of population based on the census of 2018. We also have the division of the blocks and the sites of interest of the geostatistical framework. We also have cadastral information as well as collaborative cartography in order to determine what public spaces and open spaces were public as such. Open spaces and also private spaces, and also an indicator that was calculated since 2018. We used the Sentinel-2 of that same year. Here, we can see the data or the flow chart of this process. We use the same process for both indicators, but depending on the objective, we then derive the results for each. The first is the selection of the study area, then the selection of the satellite images, then discard the images with cloud so that we can have images that have a greater visualization. In this case, if the image is from Sentinel-2, we just then go to calculate the indexes. And if the image is Landsat, which was the case for the first indicator, we need to undergo a process which is pan sharpening, which takes that Landsat images to a greater resolution. So this is how we have homologated the resolution of both images to make a comparison of results in both periods. This is a technical process. The application of random forest and the samples for training, which is used for classification of images. If this classification is appropriate, we would make this classification of the typologies based on URBA, and for each of the indicator, we obtain the specific results. In the case of the soil consumption, the obtention of the built area in the city for 2015 and the built area for 2020, as well as the calculation of the rates and indicators as it is defined. And in the case of 11.7.1, we obtain the public spaces based on the official information. Then we complement them with all these alternate sources. It is important to use OSM there, which is an important source there, which is very relevant because of the capacity of updating. We obtain the streets and we then make the calculation of the indicator with the formulas that have been established. This is the algorithm used, the random forest algorithm, which is supervised classification that allows dividing the classification in several trees, in several trainings, obtaining more preciseness for the areas. The classification is solved with some polygons where we take the training samples, 30 for training and 30 for validation, and we make a validation, which is then validated with the indicators and the matrix that is applied in the classification models derived from machine learning. Here we see the formulas for calculating the indicators. These formulas have already been defined in the metadata by UN Habitat. So we calculate the population growth rate considering the two terms of interest, 2015 and 2020. We calculate the soil consumption based on the classification. We determine the built area for 2015, 2020, and then we make the coefficient between these two rates in order to get this rate of soil consumption. For the indicator 11.7.1, this is the formula that has been defined, the global indicator, which is the one determining that area which is used, which is defined as open space. Open space is the sum of open space considered green areas, plazas, plus the surface destined to the streets over the total built area. That will give us a percentage of the area that is dedicated to this open space compared to the built area. Now, we also have this disaggregate indicator to calculate the people that would have access regarding those public spaces. And so for that, we would carry out another process based on the grid analysis or accessibility analysis. We would determine those group of people by gender or age or disability, which would have access to these public spaces over the total of people who are within the whole population or all the urban area. These are the general formulas used for making the calculation of both indicators. And this is defined in the metadata of each of the indicators. Here we see an example of how we get to determine with the satellite images the classification of each element that is required within the calculation of the indicators. This for the city of Cali, Colombia. First, we need a mosaic of images of medians that allow seeing the construction of these images around the city. Then we make the initial classification of the image, which would show us the built area, the non-built, and the bodies of water in the different colors. And then applying the GURBA methodology, this is what would determine the context area, or the area with which we would make the calculation of the indicator, which is what you see here in this color. This is the urban area or the built area for the city of Cali. Then we determine the green spaces or the open public spaces in the city, the space destined to the roads, and these two are combined in order to determine the open public spaces. With these two spatial images, we determine the areas of accessibility that the people would have. In this case, it is defined as areas of closer than 400 meters on foot, and this is how we make a geo-representation of the census, and this is how we determine the population that would have access to these public spaces. Here, we see the same images for the city of Medellin. First, we have our mosaic of images, then we have the initial classification of what is built area or built areas and non-built and bodies of water. Then we apply the methodology of GURBA in order to determine which is the built area of the city. The green areas or the green zones, once again, this is based on cadastral information, and also the area here destined to the roads, as well as the other image that has the areas of service. And with this, we can determine the number of people that could have access to these open spaces. Here we see these examples in the maps. These were the results that we have for some cities regarding the indicator of SDG 11.3.1, which is the comparison of the soil in one term. In this clear color is the soil consumption for this city for the year 2015, and in red is the soil consumption for the year 2020. What we see is that this is a overlaying, and you can see how the soil use is increasing in the outskirts, and you can also see the urbanization being increased in the cities in this term 2015-2020. With the indicators, we can then determine if the consumption is stable or unmeasured, or if in fact there is no actual expansion of that consumption, but perhaps a phenomenon related to densification. This is what we detected for 5 cities in this universe of cities. And this, you see the calculation of the indicator, where you see that in a general way, a big part of the cities have that are in the interval of 0 to 1, which is the interval recommended by ONU Habitat for having a good control of, to determine that the soil consumption is controlled based on the population growth. But if this indicator is greater than 1, we would now detect unmeasured growth in the cities compared to its soil consumption. Here we have a city like Barranca Bermeja, which I showed you in a previous image, which has a consumption which is greater than 5. This can guide the decision makers in order to take measures regarding how to ensure the sustainable growth here. We also found some cases with negative population growth. This means that the population is not growing but decreasing. In this case, we had 2 cities where the indicator was negative. And if we take this universe and make the calculation, I mean, if we calculate the value at a national level, it would give us an indicator of 0.436, which would be within the range defined by UN Habitat as a stable population growth. But for the focalization, we realized that in every city, we would have to start analyzing that behavior, specifically in those where the consumption is over or greater than the UN value. For the next indicator, as I said, we calculated a sample of cities, which is the ones that you see on the list. What we make is a sum so that we can then make a division. So we can see how the public space that we calculated with DANE plus the public space that we obtained with OpenStreetMap, which is a source that helped us to complement our data, plus the area used for roads. All these three columns would sum up and determine the public open space, which is divided by the urban area of every city, and then we can have the amount of open public space, which is public. Carlos, if we can please wrap up so that we can have enough time for the Q&A session. Thank you. Yes, I'll just take 2 more minutes. So here we can see that the indicators are between 23 and 45%. ONU Habitat recommends to have a 30% as a minimum rate. Some cities comply with this, some others don't comply with it. Here we would have population percentage that would have access to these public spaces. In some, it's less than 70%. In some others, it's greater than 90%. This is how the disaggregation allows seeing some specific cases that should be addressed in order to achieve the SDG. At a national level, we would have more than 80% of the population that is having access to these public open spaces. And to conclude, well, we can see here that currently, with a great variety of satellite images and data, it is possible to make a calculation of these indicators. Even though these images are of low and medium resolution, we can have indicators of good precision, because with these resolutions, we can get to make these type of calculations. The machine learning classification algorithms are also being used very often, which allows getting to more precise classifications. And this is a technical recommendation that we make at DANE. The integration of these geospatial and geographical information is important for making this SDG indicator calculation. And based on the UN Habitat methodologies, we will update the indicators in Colombia based on what has been modified in the methodology and with the new data sources that we have available. We hope to do that as of this year. Thank you very much.
Muchas gracias, Carlos. Carlos.
Thank you, Carlos.
Tengo aquí.
All right, so here I have a colleague. This is a question for Luis Gerardo. I will first transmit these questions to Luis Gerardo. Please let me know if I'm missing any other question, Andrea. Maria Chica is asking if level 5 of detail can be used for downloading the data, and also if the grid presentation applies criteria in order to ensure the confidentiality of the data. Purcell, those are the questions for Luis Gerardo. Please go ahead. Well, the first question from Maria Chica. Yes, not only in level 5, you can pull information from every level that is published without any problem. And it can be, well, and this is linked to the next question about the criteria that we apply. We do apply criteria for data confidentiality. For using the grid, we had a strong exercise with the statistical colleagues in order to check several scenarios and see where there wasn't any possibility of violating this data confidentiality. So the result of this very deep analysis was to get to level 10. If we got to level 11, we would have problems. So we decided to go up until level 10. What it is clear is that depending on the census level, the level will be different. Perhaps there could be an event where the level 7 or level 6 is the maximum, and that would be it. What is important is that it will always be consistent with the rest of the data. So in the case of those two censuses, it was up to level 10. And about combining the grid with the satellite images, yeah, that's possible. We are working right now so that our data cube is being reprocessed, and that's a strong work so that the quadrant that the people can get from the data cube coincides with the quadrant in the grid. So the people can make a complete and thorough analysis, both with the grid and the cube, talking about a geographic space. We're also working on that. Those would be my answers. Thank you. Thank you, Luis Gerardo. There are a couple of questions for Carlos as well. Stephen Howe is asking, how have you developed this training data? There is another question for you. Well, they're asking, what software are you using for this processing? And that's asked by Hans Rojas. And Grace Palma is asking if you have tried using the support vector machine. And another question for you, Carlos. What data was used in order to produce the degree of urbanization? Perfect. For the first question, the training samples were based on hand-traced samples that allow determining the main uses. So we made these tracings to determine what was a built area, the green zones, and bodies of water. That's how we worked with the training samples. About the next question regarding the software that we use for those indicators, we started with Google Energy. Currently, we are trying to do a migration with Python language with Colab, but we are still using Google Energy for this classification. About this vectorial support, well, we still believe that the random forest, and since it is not as robust, so we can handle the processing with this. But for other indicators, such as 11.1.1, which is about inappropriate housing, for that case, we are doing some testing with deep learning methodologies, because in those cases, we need to make a more precise reclassification, and perhaps in there, we use more robust methods. And also about the degree of urbanization, well, the defined methodology, which is also based on the use of grids, and it is linked to what Luis Gerardo said, we are also applying grids. This uses a population grid as a basis, and with this population density data and population size, we determine the GURBA methodology. This methodology is open to the public, and Eurostat is the one that has this methodology open, which is used in these two data sources, population density with the grid and the population size as well, to determine the universe of cities and the specifications that are managed by GURBA. Thank you, Carlos. I don't see any other questions, Andrea. There are no other questions in the chat. Am I right? You're muted. You're muted, Andrea.
We don't hear you.
Yes, you are muted. Can you unmute
Now?
there? Yes, we can hear you now. Yes.
Okay, thank you, thank you. There is one at the beginning, the first question Maria Chica has made. I am trying to find it now, but I collect that. As los datos estão en la nube a nivel de Open Data? Foi a pergunta de Chica para Gerardo.
Sí, muchas gracias. Sí, eso iba a decir que esa pregunta.
Thank you. Yeah, I had also seen that question at the beginning. Not now. Now everything is supported at the Institute, but we are analyzing with the technology, our IT colleagues, because the leap that we will make to Sentinel will force us to have to go to the cloud because of the amount of data. But right now, it's not in the cloud, it is at the institutional structure. Thank you very much. I think that we have reached the end of the seminar. We wanted to thank both speakers, and we also want to thank Andrea. I think that this webinar, this first webinar, is routing us towards the event in November, the event that we will have in November, the World Data Fest. And I think that the information that we could see here from Mexico and from Colombia gives us many ideas on how to work jointly with the big data group that is coordinated by Andrea in that sense. So from CEPAL, we are very interested on this, and we are trying to find a way to link the data more and more. We just had a couple of weeks ago good news about a potential collaboration with the Operations Center of Copernicus in Chile, with the University of Chile, and we will be able to work in 3 topics that are fundamental for us and for the region, for Latin America and the Caribbean. Therefore, we will have all that European information for, well, topics related to soil use regarding coasts and seas. The coastal issue is fundamental for the Caribbean as well as for the coasts of all Latin America and for the cities as well. So we are working on that collaboration process in order to join all the data, satellite images, and to be able to build on all this so that we can have a basis and have indicators for these SDGs so that we can generate and produce many more indicators that can be used by the cities and the regions. Without further ado, well, Andrea, I don't know if you have any final remarks.
No, just thank you, Luis Gerardo, thank you, Carlos, and thank you, Orlando, for being here and for sharing this first webinar, and hope to see you all at the next webinar. So have a good day.
Gracias. Solamente comentar que tuvimos 180.
Thank you. I just wanted to say that we had 180 attendees in this first webinar, and we hope to see you all in the next one. Thank you all. Have a great day. Goodbye. Till next time.